So what we're going to start in this chapter is something called stoichiometry. And stoichiometry is a big fancy term for converting one unit to another in terms of chemical reactions. Now this is really important because this is how we figure out how many of each atom actually reacts with each other. Unfortunately, because atoms are so small, we can't actually count them out. So what we do is we actually weigh them out. And then what we do is we assume, for purposes of counting, that they each have the same weight or mass. So here's what this looks like, okay? What we're going to do is we're going to calculate relative atomic mass. And what I mean by relative is that we compare them to each other. And the one we're actually comparing them to is carbon-12. Now what we do is we say that carbon-12 is our standard. And we're assigning it a mass of exactly 12.000 AMU, okay, atomic mass units. And so what we're doing is we're going to compare the mass of hydrogen to carbon-12. The mass of oxygen to carbon-12, the mass of nitrogen to carbon-12, okay? The way we do this is using a mass spectrometer, and what that actually looks like is this little diagram down here. We inject our sample into the mass spectrometer, and we vaporize it. When we vaporize it, we're going to pass it through an electron beam. And what the electron beam does is it kicks out some of the electrons from our original sample, and it turns them into positive ions. Okay? So we had an original element here, kick off electrons, turn it into a positive ion. Now we're going to speed it up, and so they're going very, very, very fast when they hit this magnetic field. And what this magnetic field is, one side is going to have a little negative charge. One side is going to have a positive charge. If the magnetic field was not here, my ions would continue going straight. But because my magnetic field is here, I'm going to change the direction of my ions. Here's why. I have positive ions. Like charges repel, opposite charges attract. So what's going to happen is this positive plate is going to push on my positive ions so that they move away from it. My negative plate is going to pull on my positive ions so that they move toward it. Okay? But not all of my ions are the same speed. Some are going to be larger than the other, okay? So they're all going to be pushed and pulled with the same force. It's really easy to move light ions or light objects in general. And so the things that are the lightest are going to move or be deflected the most. The things that are the heaviest, it's hard to push, it's hard to move, and so they're going to be deflected the least. So what's going to happen is all of my ions are going to be sorted by mass, heaviest to least, okay? So let's go ahead and fill in our blanks that we explained. We're passing them through high-speed electrons. It's going to turn them into positive ions. The ions are passed through a magnetic field. And then it's going to separate them, and it's important that you know this part, separate them based on mass. That's why we call it a mass spectrometer, okay? So the heaviest particles move the least, the lightest particles move the most, okay? So this is how we figure out what makes our sample up. We can figure out how many of each of our isotopes are present in a pure element, Or if we had a mixture, we could figure out what the mixture was actually made of based on mass. Okay? So what we're finding is the average atomic mass. And here's the important part. It's a weighted value. And this weighted value is based on the percentage of naturally occurring isotopes. So remember, isotopes were atoms of the same element, same number of protons, same number of electrons, but they have different neutrons, and so they had a different mass. So we could have something like carbon 12, carbon 13, carbon 14. Well, when we find the average atomic mass, I don't just add up all these numbers and then divide. I need to figure out how much of these I have for each isotope. And that's where my mass spec came in. Okay? So this is what the data looks like for our elements. Okay? Here we've got neon. And so by looking at my data, I can tell that neon has 3 naturally occurring isotopes. 20, 21, and 22. There are no peaks here, and so there were no isotopes there. It's got 3 naturally occurring isotopes. Okay? Now, what the data will actually look like is it'll look like a table like this. Okay? So it tells me relative numbers of atoms. Sometimes this will say percentage of atoms. So 91% or relative number of atoms of 20. Here we've got 0.3 of 21, and here we've got 9 of 22. Now if I were taking a regular average, I would just say 20 plus 21 plus 22 divide by 3, and my average would be 21. But that's not the way this works. Most of my atoms weigh 20, so my mass has to be closest to 20. Okay? So here's how we do this. Here we've got our example. So when natural copper, so this data table's for copper, is injected into a mass spectrometer, the results shown below are obtained. Use the data provided to compute the average mass of natural copper. So I've got 2 isotopes for copper, 63 and 65. Okay? Now these are estimates. Copper 63 doesn't actually weigh exactly 63. It's 62.93. Copper 65 doesn't weigh exactly 65. It actually weighs 64.93. Okay? So again, I've got my relative numbers or percentages. It's basically the same thing. Okay? And I need to figure out the average. Now, before I do any math, I can already tell that I should have mostly copper 63. It's my highest percent. So when I finish my math, it should be closer to 63 than 65. So here's what I'm going to do. There are 2 different ways I can do it. I've got 69.09% and then 30.91% of each of my isotopes. Now what I'm going to do is I'm going to change my percentages to decimals by dividing by 100. So instead of having 69.09, I'm going to have 0.6909. Same thing here. This becomes 0.3091. I'm going to take those numbers and multiply them by their respective masses. So I had 69% of this one, and I had 30% of this one. So I'm going to multiply those values. Okay? So I'll get 43.478 for my first one. I'm going to get 20.0698 for my second one. Once I've multiplied each by their percentage changed as a decimal, I'm going to add those up, and I get 63.5482. This is my mass, so it would be AMU, or atomic mass units. If I look at my periodic table for copper, 63.546, pretty dang close. Okay? So I said there were two ways. I can either change this to a decimal first, or I can multiply the 69.09 by the mass and then divide by 100 before I add them. Okay? It doesn't matter which order we go in, but I always have to do these steps to figure out the weighted percentage. Okay? So it's important to remember the number on the periodic table depends on the percentage of our isotopes. It's the relative or weighted average based on the percentage of each isotope, and we get those numbers from our mass spec.